All right, we'll keep allowing folks to trickle in, but in the interest of time, I will start. Okay, welcome everyone to our 49th ECS and Cloud Feedback Virtual Symposium. Today we have three speakers, as we're wont to do. We have Ed Blanchard-Wrigglesworth from the University of Washington, Leif Fredericks from Colorado State, and Cristi Proistosescu from the University of Illinois at Urbana-Champaign. Um, As many of you who have joined these before know the setup for these meetings, we have three short talks around 15 minutes with questions after each. And if there's time, we'll have a short general question and answer session after the last talk. Please type your questions or comments into the chat at any time. But if you want to vocally say them, just wait till the end of the talk. And then if you're interested in giving a talk in the future, please reach out to myself or other members of the executive committee up here. We're always looking for speakers for the next symposium. And if you'd like to see any of our past talks, sign up for our mailing list, what have you, please check out our website. So today we're going to start with Ed. So Ed, do you want to try to share screen here?
Yes. Okay, so hopefully everyone can see this.
Looks great. And I'll give you like a 2-minute heads up.
Awesome. Well, thanks, Matt, and the committee for the invite to give this talk. The title's How do increasing boreal wildfires impact global and Arctic climate trends? And I especially want to thank Patricia De Repentini at the University of Ottawa and Doug and Frison at the UW for my co-authors on kind of the first part of this study, and then this longer list of collaborators is for current ongoing work that I can highlight at the end. So I want to start by showing a time series of biomass burning emissions in the boreal region. These are annual totals averaged between 56 degrees north and 70 degrees north, which is essentially Siberia, Canada, and Alaska. And I'm showing here black carbon, but this is just as a proxy of all biomass burning emissions. There's many other species that get emitted, such as sulfur dioxide or organic carbon. And here I'm showing in red the satellite estimates and observations from the Global Fire Emission Database between 97 and 2014. And in blue is how CMIP6 models were forced. Now CMIP models don't use active fire models, so you need to prescribe these emissions basically as a forcing to the models. And you can see that between 97 and 2014, there's perfect overlap because CMIP is using that observational period directly. Prior to 97, we had proxies of these emissions, and you can see that the average values are similar, but there's a lot less interannual variability. For the 21st century runs, this is for those future scenarios from 2015 onwards. This is what CMIP6 used, which is essentially a pretty flat climatology. And I'm showing only here to 2060, but these would continue the same to 2100. When you look at the updated observations, add in the period between or after 2015, this is now the observed pattern. And we've had a huge increase in boreal wildfires, both in Canada and in Siberia. And this increase has been tied to warmer summers, warmer springs too, with an earlier snow melt, increase in lightning, and even less sea ice. So all factors that we expect to continue. So at least in the sort of wildfire literature, these sort of trends or patterns are expected to continue. And I haven't seen anyone argue that this is just a short-term blip and we're going to go to low value. So we sort of observed this, and Patricia had done some work showing how important these emissions could be. And we're very curious about this and what impact this might have on climate trends in the near future. So we've seen this 160% increase kind of in this later period compared to the prior period, and already a very quick divergence between CMIP6 or how we're forcing CMIP6 models and what observations are doing. Interestingly, outside the boreal region, this is the same analysis, but south of 56 degrees north. and we can see that there's much better agreement, right? So the boreal region is this kind of very special region where wildfires have strongly increased, but we haven't taken that into account in CIMIC models. So there's another factor that we've observed in observations, and that is that we've observed, we're fairly confident that there's been a really strong increase in the summer aerosol optical depth over the Arctic and boreal regions in the summer. And this top left panel, I'm showing here, these are the trends in aerosol optical depth between 2003 and 2020 in Zhang et al. 2024. And the bottom panels are a figure in our paper where we update it to 2023. And in the bottom left, this is a composite difference between the mean summer aerosol optical depth over the last 10 years, more or less, and the prior period. And you can see very strong increases in over Canada, Siberia, and into the Arctic. If you take the zonal mean, this is pretty much the only region in the world where aerosols have been increasing or consistently increasing. We see a decrease over China. That's mostly because of the clean air legislation. And on the right is a time series of the mean summer aerosol optical depth over the boreal region and the Arctic region. So the increase in aerosols over the Arctic is quite strongly tied to Siberian wildfires. Okay, so with that in mind, we wanted to see what is the impact on climate model simulations. So we've created a new ensemble using CSM2. And what we've done is in 2015, we branch from the existing CSM2 large ensemble, and we've produced 9 new members. And we use the same 4 scenes as the large ensemble, so an SSP 370 scenario. And the only thing we change is that we ramp up the boreal biomass burning emissions over the boreal region between 56 north and 70 north, and that's represented in the dashed blue line. And we're not just increasing black carbon, we're increasing all the species that come with the biomass burning emissions, which importantly are sulfur dioxide that become sulfate aerosols and the organic carbon. So the way this dashed line is built is that for 2020, so the model in the 21st century ingests emissions every 5 or 10 years. So 2015, 2020, 2030, and then every 10 years. So for 2020, we just use the average emissions between 2019 and 2023. And then for 2030 onwards, we just use it's a very simple scenario, a sort of linear extrapolation for each month and each grid cell. So we just wanted to kind of come up with a simple, very simple scenario so that we came up with. This might, it was even argued to us that this might be a conservative scenario because these wildfires have been tied to the exponential of summer temperature in boreal regions. But if you fit an exponential, you run out of forest by 2040. So there's the important negative fuel availability feedback. So we don't think that pace of increase is really sustainable. And then the other implication of this scenario is that we have by 2060 or most of the scenario, they are precedented by 2023 in observations, right? So we already have evidence in observations that we can have these really high emissions. The other thing to focus is that we only run the simulations between 2015 and 2060. This is mostly because we want to focus on sort of that near-term trends, kind of decadal timescale, because I think there'd be a lot of uncertainty on what these wildfires might look, that far into the future. Okay, the other thing to note is that there's really strong seasonality to these aerosol emissions. Wildfires in the boreal regions in the summer, they peak in July. This is the seasonal cycle of the emissions. And you can see in red and blue, those are the historical emissions. And then the dashed is this new ramped, right? So there's no change in the cold season, and we're just increasing that aerosol input in the summer months. Okay, so now into the results. This is the mean annual temperature in the control large ensemble, shown in black and in gray. In black is the ensemble mean, and then in red is the new ensemble that we have 9 members. So the bold red is the ensemble mean of those 9 members, and you can see that where it's highlighted, the ensemble mean is highlighted with the black edges. That's where it's significantly different to the CSM2. So you can see there's a slight reduction in global warming trends of about 12%. so a slightly weaker warming. And this is particularly strong in northern latitudes. So I'm showing here the same time series, but for Arctic temperature, this is north of 70 degrees north, where we see a reduction of about 38% in the amount of warming. So pretty, like a pretty significant reduction. When we look at the spatial trends of the changes in temperature, here I'm showing the default CSM2 light ensemble in the middle panel, and it has the typical patterns of warming that I'm sure we're all familiar with quite strong Arctic amplification. You see the warming hole in the North Atlantic. You see land warming slightly faster than ocean basins. And in the left panel, I show the boreal fire patterns, and perhaps the more useful panel is the one on the right, which is the difference between the two. So you can see much slower warming over the Arctic regions, northern land masses, and then also over the North Pacific and the North Atlantic, north of about 20 or 30 degrees north. There's no temperature change in the southern hemisphere, which will be an important feature to remember later. There's also a very interesting seasonality to these differences. So remember that I mentioned that we're only increasing the aerosol emissions in the summer, and these go into the lower troposphere. They are forced into the model. They actually go into the lowest level of the atmospheric model. And because they're tropospheric aerosols, they don't have a very long lifetime. They're not like stratospheric aerosols, right? So after a month or so, you see that the burdens in the fall kind of go back to control, right? So in the winter, there's no more, the atmospheres in terms of the aerosol loads look the same. But when we look at the temperature differences, in the summer, we see that the relative cooling is focused over the northern land masses where those wildfires are. So you can see Canada and Siberia there. And in the winter, however, we see most of the cooling over the Arctic Ocean. And you might be wondering why, if by the winter you have no more differences in aerosols and there's no shortwave. Um, and the mechanism here is that you get a reduction in ice melt in the summer, and that thicker ice and more extensive ice cover persists into the winter. And this cooling in the winter is then forced by that greater ice. So we see this sort of delayed response through the year to this summer aerosol loading. Onto changes in precipitation. I show those on the left panel. These are annual differences, and where there's stippling, that's the significant difference. And there's two main patterns. One is that there's a slight southward shift of the ITCC that is highlighted by the panel on the right, which shows the zonal mean in the precipitation difference. And this is consistent with something we've known over 20 years, like the Chang and Bitts paper, that if you warm one hemisphere relative to the other, the ITCC shifts to the warming hemisphere. And in this case, we're cool in the northern hemisphere, relatively cool in the northern hemisphere, but no change in the southern hemisphere. So we see that shift south of the ITCC. It's not massively strong, but it is when you take the zonal mean, it is significant. And then the other pattern we see is that the Arctic becomes drier relative to the control. And this is probably just tied to the thermodynamics, where we know that a warmer Arctic is a wetter Arctic. So if your Arctic warms at a slower pace, it will become wetter at a slower pace too. And that's pretty consistent in these results. The other change we've looked at are the changes in sea ice. And because of the aerosol effect and the cooling in the summer, we see a more extensive Arctic sea ice extent. And this is year round. I show the annual time series on the left and the September sea ice extent time series on the right. One thing that we focus in the Arctic communities, thinking about when the Arctic becomes ice-free by the end of summer, and that's normally quantified by the September sea ice extent dropping below 1 million square kilometers. And you can see that in the CSM2 large ensemble that happens around 2040 or the early 2040s, whereas when you ramp up the boreal wildfire emissions by 2060, you still have 2 million square kilometers. So it has a pretty big impact on the timing of a sea ice-free Arctic in the summer. And then finally, I do want to mention this. This is work in preparation with Camille Hankel. We've had a bit more look at the North Atlantic. One thing we notice is that the only region in the kind of northern latitudes that doesn't show a difference in temperature is over the subpolar gyre in the North Atlantic. On the top panels, I'm showing the temperature differences between the wildfire emissions and the default CSM2 light ensemble, and you can see that black box. That's the trends, temperature trends are the same, and what we think is happening here is that there's actually negative feedback whereby in these runs, in the wildfire ramped emission runs, the weakening in AMOC is weaker. That is shown in the bottom left. That's the time series of AMOC. CSM2 has a very strongly declining AMOC trend that is shown in the red time series, and the trends shown in that right panel in the bottom row. And the decline in AMOC is much weaker in these new runs, and we think that serves as a negative feedback. So you have the relative cooling from the aerosols, but because you essentially have a stronger AMOC that counteracts that. And so we see that the how AMOC responds to these aerosol emissions is having an impact on the regional climate response. We're looking at this in other GCMs that show different changes of AMOC, and we do see a pretty big difference in how the temperature trends in this region are simulated. Okay, so in summary, these boreal biomass burning emissions have increased massively in observations. We expect that increase to continue, and this has not been taken into account in CIMIP models in the past. CIMIP 5 did the same. I know the CIMIP 7 forcing files just came out. I haven't had time to analyze them, but I'm really curious to see what they look. And at least from this early result, these emissions could have a pretty significant impact on at least sort of decade-old climate trends. This was published, or we published this last year, and there's the reference at the bottom. And I do want to point out kind of what work we're doing following this. So we're studying the impacts on AMOC. Camille's leading that, but we're also running the same simulations with other GCMs. So we've got results with ECR3, E3SM, version 2, KenyaSM, and NOAA, GFDL, and NASA GIS have just joined us. And we also want to think about the sensitivity to forcings if we added internal variability to that forcings, or if we have an increase in wildfires followed by a decrease due to maybe, humans or society taking a more proactive role at fire mitigation. It'd be interesting to see what impact that would have. And also mention that we didn't change the land type in these runs. And we know that when boreal forests burn, there's changes to the surface albedo. And I do also want to point out that the actual increase in CO2 in these scenarios is fairly modest. And I don't know how I'm doing from time, Matt.
Yeah, so we should wrap
All
it
right.
up here, Ed.
Okay, so that is, thank you very much.
Sweet. So we have time for probably one question that can be asked, and then anyone else can throw something in the chat. So if anyone wants to raise their hand, please feel free to ask a question. Eric, if you want to unmute yourself.
Yeah, thanks, Ed. This is great. I guess I'd wondered how much do we really know about, what happens to the forest? I mean, assumption seems to be that every year the forests burn, they'll just grow back, and so you can have the same fire in successive years. And I wonder, do we really know, what the limits are on that?
That's a really good question. And I'm certainly not a forest ecologist. But from what I understand is that the replacement timescale of these forests is in the kind of 30 to 80 year time span, right? Because it takes time for the forest to regrow. You can also have like species substitution where like you'll have a certain species of tree, like say black spruce burn, and it might be replaced by alder or a different type of tree. And I know different trees have different characteristics in terms of their fire susceptibility and even the amount of how big the fires are likely to be also depends a little bit on forest species. Now, the main thing that I think will play a role is, and I mentioned it briefly in terms of how to set up these scenarios, at least until the point where we have the active fire models. And I know a lot of people are working on introducing active fire models into the climate models. But there's the aspect of the fuel availability feedback, and this is a negative feedback. And it's very simple, right? If you burn all the forest, there's no forest left to burn. And so this would be a strongly limiting factor, at least, maybe at those longer time scales. I do want to point out that Mike Wallace just published recently a paper looking at just the amount of biomass in the boreal regions. And what's interesting that you might expect that the amount of boreal biomass may have gone down, right, over the last 10, 15 years as we've had that really fast ramp up in the wildfires. But what's interesting is that the regions that haven't burnt, which is still the vast majority, right? If you integrate everything that's burned, I think it's in the 5% sort of ballpark. So the 95% of the forest that hasn't burnt, the biomass has actually increased, partly because of the CO2 fertilization effect, warmer temperatures, so better growing conditions. And, there isn't much human interaction. A lot of these regions are very remote, but I believe that in some parts of Siberia, there has been less, sort of human human management of forests. That I think some forests have increased. So there's still a lot of biomass, but I think these questions of the biology are pretty crucial to understand exactly how these trends will evolve.
Great, thanks.
Thanks for the question, Eric.
Cool. So Ed, if you want to keep your eye on the chat, if anyone has any other questions for you, but let's just jump right into Leif now. Thanks for the talk.
Cool. Okay. Is this showing up?
Yeah, looks good.
Great. Thanks for having me. Thanks to the committee for letting me join today. My name's Leif. I'm a PhD student at Colorado State University. I work with Maria Rugenstein and Dave Thompson. Today I'm going to be talking about some work that we've been doing about moving a bit beyond the Green's function to try to incorporate data-driven methods as well to quantify the pattern effect. So just as a bit for organizing the talk, some key points I'm going to hit. First of all, go through a bit of the history of the pattern effect and discuss what the Green's function allowed us to do and why it was a huge step forward for us in exploring the pattern effect. And then talking a bit about how now there's been a bunch of methods moving this forward to try and estimate these statistically as well, so to get at some of the same information, but from a different angle. And the thing that makes that exciting is that we can ultimately bring this to observations and coupled systems. So just to start off, a brief history of the pattern effect. In this case, in this talk, I'm going to be talking about R in the typical energy breakdown. So in this, N is the net top of atmosphere radiative imbalance, and that can be decomposed into F, which is the radiative forcing, and R, which is the system response to that forcing. We break this further down into where R is a linear feedback to the change in surface temperature, modulated by a feedback parameter lambda. One problem with this setup is that over time, especially if you equilibrate climate models and let them actually run to climate equilibrium, this feedback parameter tends to change in time. So what we see in the top right is it's becoming less stabilizing as we get closer to equilibrium. And we've realized that this is connected to the pattern of sea surface temperature warming. And so if we look at the earlier period, the warming pattern sets up a feedback parameter that's more negative and so more restoring. But then with time, like later into these simulations, the feedback parameter is a lot less restoring, and this is connected to the pattern of the surface temperature warming. And so what the Green's function method allowed us to do was to start to connect some of these local changes to non-local feedbacks. So what is done in these Green's function simulations is you have these SST forced simulations where you just warm a single patch of the Earth's surface, and then relative to a control with no surface warming, you can see what the radiative response is spatially, and then also what the global mean radiative response would be to a temperature perturbation just in that patch. And so you can see in this figure the effect of warming in different patches across the Earth's surface. And so what this allows you to do is to build a sensitivity map, which is what I'm showing in the bottom right. And what this means is if you were to warm any point on the surface by changing the local temperature, this map is showing the effect that you would get on global radiation in response. And so this is sort of a sensitivity to the spatial pattern of warming. And you get this by performing these same patch experiments over the full global ocean. And this allows us to have a lot of simulated insights into why historical and early period feedback parameter differs from the future feedback parameter. And from these simulations, we also get a connection to physical mechanisms that we understand. So for example, if you were to warm areas of tropical ascent, this tends to stabilize the free troposphere through warming, and this sets up conditions for low, highly reflective clouds. So you see that these regions of deep convection tend to be negative feedbacks, as is shown in the bottom right. Conversely, if you were to warm areas of subsidence, this has the opposite effect, destabilizes low clouds, and produces a positive feedback from warming in these climatological regions of subsidence and low clouds. And extratropical forcings tend to affect the circulation. But then the question is, how far can we get? So what we're showing here is from the Green's function MIP, a bunch of different results from running Green's functions in different models. But ultimately, our goal is to bring this back to observations. We want to understand how these connections are playing out in the real system. And we can see what the models give us, but the question is, how far do we believe these models to be telling us the truth about what would actually happen in the real world? There's a few other caveats to the Green's function. As it's currently setting up, it's only done with SST forcings, so we don't include the land feedbacks in this. Coupled behavior for the same reason can't be captured because we're forcing the sea surface temperature boundary. These patches don't really have a realistic pattern of temperature. It's just a single blob of temperature change. This creates strong gradients near the patches, and we don't see coherent modes of internal variability ENSO. The Green's function can't really capture what's happening in the patterns of warming that actually evolve in the real world. And this is kind of a brute force approach as well. It's just looking at temperature at every single location and backing out what the response is. But our question is, can we be more efficient in how we do this? And with that, can we use data we already have from, say, coupled pre-industrial control or coupled simulations? So to get at that, we think of these local temperatures then as predictors instead. So these would all be predictors on the global radiation. And in the Green's function setup, each of these, the value at each location is the partial derivative of global radiation to temperature change at that location. But we could reformulate this as a multilinear regression problem as well, where the values at each location would be the coefficients on the local temperature predictors for each of those. And so what I'm showing in the bottom right is an attempt to do that with ordinary least squares multiple regression from Jonah Block-Johnson in 2020. And this gives you a sensitivity map similar to the Green's function. You can see that it's kind of spatially noisy, but you get some of the same features that you might expect. However, more broadly, the data-driven Green's function approaches have become a lot more popular in the last few years since that first paper. And in a paper that was just accepted to the Journal of Climate, I and 11 other co-authors have been trying to compile and compare these different statistical approaches to get to these sensitivity maps. So what I'm showing here are a bunch of different maps, all trained for the most part on pre-industrial control in the MPI model. And so they're just looking at coupled internal variability to back out these sensitivity maps. And we see common features. So there are physical things that make sense with our prior understanding from the physics and from Green's function experiments. So deep convection areas tend to be negative, as we expect. And similarly, subsidence regions tend to have a positive feedback across these maps. But we also get some behavior that can't be captured by the Green's function and don't show up in those maps, like there's a positive equatorial feedback in the Pacific that's reminiscent of the ENSO signature. And so this is likely connected, because we're learning from internal variability, to feedbacks that operate through ENSO. And so to check like how much we should believe the sensitivity maps, we perform a test on internal variability as well. And so this is an out-of-sample test. These are 100 years from the same simulation that we used to train, but that the methods have never seen in their training. And then we apply these different methods to the patterned time series of temperature to get a prediction for what the global radiative anomalies would be, and compare that to the actual truth in the model. So this is an out-of-sample test on our training. And we evaluate this by looking at the correlation between our prediction and the truth from the simulation. And when we do that across the 12 methods that I showed, we find that about 50 to 80% of the variance out of sample can be explained across these different methods. And so on the left, I'm just showing the time series that broadly demonstrates that we're matching the swings in radiative response just from the temperature field. And then the right, I'm showing in correlation space how well these different methods perform. And something we found interesting from this is that 80% seems to be a fairly robust limit on how well we can predict internal variability from these statistical methods. And the top 4 methods I've highlighted here are all kind of related mathematically, but the CNN, the convolutional neural net, is a completely different approach that uses nonlinearities, and it performs well, but also seems to be subject to this 80% prediction limit for internal variability. So then this figure on the right comes from a different paper that I was working on last year. And here I'm showing, this is for ridge regression, that this doesn't only apply to MPI, which is what we've been looking at up to this point, but also to other climate models as well. So this 80% thing seems to be, at least in models, about the limit of our predictive ability. And then to match what's been done in prior investigations into the pattern effect, we're also going to look at an out-of-distribution test. So looking at how well these methods perform on 4 times CO2 forced experiments. So again, we have the spatial time series in temperature, and we pass these through the different prediction methods and end up with an estimate from the methods on the radiative response to the 4 times CO2 forcing. And it's worth pointing out at this point that this was not the goal of these methods. They haven't been like calibrated or targeted to predicting the force response. This is just us looking at how they perform after having trained just on internal variability to see what they do when exposed to 4 times CO2 temperatures. When we do that, the methods that I would categorize as broadly linear tend to slightly underpredict the strength of the radiative response in 4 times CO2. But then if we look at methods that have nonlinear elements in either training or prediction, what we find is a little less predictable, like whether an individual method will over or under predict the strength of the radiative response. And then so in this case, we're also showing the Green's function as a point of comparison. But in these methods that use SST warming simulations as part of the training, we find that they tend to overpredict. But the really important caveat here is this shouldn't be taken as one method being like quote unquote better than another, or like an in-depth exploration of their ability to predict the force response. It's just to point out that from more or less the same training data, these methods, which even have similar features in their maps, all predict very different responses in a forced situation. And it should be noted that there's not really a correlation between how well they perform in the internal variability and how close they are in the force response to predicting the magnitude of the radiative response.
2 minutes.
Thanks. So the last thing I'll touch on is kind of the most exciting things about these methods, which is that we can use them on the observational record. So on the top left, this is from 24 years of series and era 5 data, and this is using Ridge and Lasso on annual values. And we see kind of the same features we might expect. So areas of deep convection have negative feedbacks. This is true also over the land. We're using near surface air temperature here, which is another advantage relative to SST Green's functions. And then we have positive feedbacks in areas of subsidence. We see this equatorial ENSO reminiscent feature as well in the observations. And in the bottom left, this is a slightly different method, maximum covariance analysis applied here to monthly data instead. And this really highlights this subtropical cloud deck area as a positive feedback. It also indicates that land might have a strong negative contribution to the overall feedback. So these are fairly exciting that we can now look at what the sensitivity maps might look like for the real system. It's worth pointing out, though, that on the right, this is the rest of that figure that I kind of previewed. In this, this is all in internal variability, but I've pulled out 24-year periods to see how well they do at predicting internal variability out of sample. And there is a significant decrease in predictive skill when you have a limited sample size. So the maps on the left, we can interpret as doing a good job of capturing the feedbacks and connections that really did happen over the last 25 years or so, but these may not necessarily represent the full range of internal variability of the real system. So with that, I'll just leave my summary points up on the screen and I can take questions. Thank you.
Great talk. Thanks, Leif.
Thanks.
We have time for a question or two. Cristi, want to unmute?
Yeah. Hi. Maybe I missed this, but are you using large ensembles of AMIP type simulations? Because
Sorry.
because if not, there's stochastic atmospheric variability that is not forced by SSTs, which is going to give you an inherent limit of how much of the radiation in the test sample you can predict.
Yeah, so these are all trained on just pre-industrial control, so from coupled simulations, but using 1,000 years of training. And so the idea is that we probably see like a variety of situations corresponding to similar sea surface temperature arrangements. So we're probably sampling a decent amount of the variability in the atmospheric response just from the size of the training data. And also in some of the other models that we tested this in, we had over 5,000 years to train from, and that going from like 1,000 to 5,000 didn't really seem to change this 80% prediction limit.
But how long is your test sample?
Just 100 years. But this shows up using different just breakdowns of which is the training and which is the test.
Okay, thank you.
Mm-hmm.
We have time for another quick question if anyone has one. I'll ask a quick question, Leif. Are
Yeah.
any of those methods that you suggested just kind of like unrealistic in terms of using them for studies? Like I understand you threw like kind of the kitchen sink at it here.
Yeah.
Are there any that you just kind of would not use?
There might be some that don't behave well given data limitations. So like the convolutional neural net requires a lot more data than some of the other ones. Excuse me. So for that one, like 24 years for observations wouldn't really work. But I think they all give different pieces of information. And you'd kind of just want to think about your use case and like what data you're using, and perhaps comparing between them is also useful.
Cool. Thank you.
Mm-hmm.
All right, great talk. I appreciate it. So, Cristi, if you want to start sharing, and if anyone has further questions for Leif, throw them in the chat.
Okay, hello everybody. Can you see me? Can you hear me?
Looks good. Sounds good.
Good. Thanks for giving me the chance to talk about this. This is a little bit of a strange little presentation because I feel like a large number of people are going to say we know this. We've known this since the 80s, maybe earlier. But I still felt like it was a little bit important to put this out here again. This is work primarily funded by DOE, although also a little bit by NSF, and it is on archive and in review at GRL. So over the last maybe 10 years, the field has sort of converged on a paradigm for the pattern effect, a fairly simple explanation. Right? And this is a partial quote. For every complex problem, there is an explanation that is clear and simple. And what we've mostly learned, and Leif's presentation highlights that as well, is that warming patterns that have more warming in the West Pacific and less warming in the East Pacific tend to lead to more low clouds and a more negative feedback. One of the first papers to highlight this is Zhu, Zelenka, Klein, 2016, where they show these are trends in AMIP simulations that show this pattern of cooling in the East Pacific and amplified warming in the West Pacific. And these are corresponding trends in low cloud cover and these AMIP simulations that show an increase in low cloud cover over the East Pacific, over the equatorial East Pacific, and over the subtropical East Pacific low cloud decks. This also shows up very nicely, as Leif pointed out, in Green's functions summaries of the pattern effect. So if you plot the impact on global radiation of local warming, you find that if you warm in the West Pacific, you get a very negative global response. So the deep blue here means that if you warm here in the Indo-Pacific warm pool, you get radiation out to space. You get a negative radiation response. This doesn't mean that the radiation is coming out here. It just means that the global response to warming here is very negative. Okay, so that paradigm has coalesced over the last decade and is summarized here in IPCC in AR6 in Chapter 7. There's this associated figure 7.14, which is really an adaptation of Torsten Mauritsen's figure from 2016. And this is the paragraph that summarizes the current paradigm. Right, so the mechanisms and radiative effects are illustrated in figure 7.14. And just so I don't pick on this particular figure, I'm going to show a figure that I myself has shown many, many different times. So I'm also guilty of pushing this paradigm. So this paradigm is based on something called quasi-convective equilibrium weak temperature gradient. So sea surface temperatures in regions of deep convective ascent in the West Pacific warm pool govern the temperature of the tropical free troposphere and in turn affect low clouds to the strength of the inversion that caps the boundary layer, i.e. the lower tropospheric stability in subsidence regions. So in visual form, if this is the warm pool, convective quasi-equilibrium means that the temperature here is the temperature profile is about a moist adiabat, which means that the free tropospheric temperature here is strongly coupled to the sea surface temperature in the warm pool. The weak temperature gradient says that in the deep tropics, the free troposphere can sustain strong gradients. So then this means that the free tropospheric temperature in the East Pacific is also coupled to the free tropospheric temperature in the West Pacific and therefore to the sea surface temperatures. And this leads to a strong inversion and these cloud-capped boundary layers in the subtropical low cloud decks. And then we can ask what happens. We can use this framework to understand what happens when you have surface warming within ascent regions, which warm the free troposphere, increase low cloud cover, and cause an increase in emissions of thermal radiation to space, and a reduction in absorbed solar radiation. So we can go through this. So we can say, okay, if you warm the sea surface temperatures in the West Pole, convective quasi-equilibrium means that you're shifting the profile of the atmosphere in the convective regions, which means you're warming the free troposphere. Weak temperature gradient means you're also warming the free troposphere everywhere. This leads to an increase in the strength of the inversion and leads to more clouds and reduction in absorbed short solar radiation. Right. So then if you plot the Green's function, right, this is equivalent to asking what happens when you warm here in the warm pool. Right, you get this warming of the free troposphere, strengthening of the inversion in the capped boundary layers in the subsidence regions. Right, this is basically a recap. Hopefully everybody is with me on this. All right, here's the problem. The full code is for every complex problem, there is an explanation that is clear, simple, and wrong. This is a very simple explanation for the pattern effect, and it is, if not wrong, I'm going to argue at least incomplete. So this is actually something that bothered me for a long time, because if you look at past papers, so this is the CAM5 Green's function from Zhu et al. 2017, the CAM4 Green's function from Dang et al. 2019 that I was also involved in. This is the HAT-GM2 simulation of warming in the warm pool, and this is the ICON Green's function from Williams et al. 2023. And one thing that you can clearly notice is that when you warm in the warm pool, these are all responses of stability of EIS, lower tropospheric stability, or a convective index that is strongly related to EIS. What you see in all these simulations is that if you warm in the warm pool, you do not increase the stability over the subtropical low cloud decks. In fact, you decrease the stability over the cloud decks. And you see this in CAM5, you see this in CAM4, you maybe don't see this as strongly in HAT-GM, but you see it in ICON as well. And this is the opposite sign of the response from what you would expect from that QEWTG paradigm in those cloud-capped boundary layers. And if you look at this pattern, to me, this sort of screams wave trains. This looks a little, some of them looks a little bit like the Hoskins and Caroli paper. So all we did for this piece was dig in a little bit more into this using an E3SM Green's function. So these are some simulations with the E3SM v3 model. I'm going to highlight the response to 3 warming patches in the equatorial Pacific, and I guess the Indo-Pacific. And then these are plots of the climatology in the control simulation. This is EIS, so this is stability, this is low cloud cover, and then this is omega 500. Right, so you notice these regions of strong inversion, lots of low clouds, so these are the low cloud decks in regions of subsidence. And then we can look at what happens when you warm these regions and do some Boni decompositions. For example, here we're going to look at the response of low cloud cover, and we're going to bin it. So we're going to do this Boni decomposition. We're going to bin it by either the climatological values of EIS, low cloud cover, or omega 500. So if we focus on EIS on the left, the black vertical line corresponds to the thick black contour. So it separates regions with EIS above 4, which is one way to look at these strongly capped boundary layers. And what you see is that in these regions, the low cloud cover actually decreases in all 3 of these patch responses. So when you warm in regions of deep convection in the Indo-Pacific warm pool, you actually decrease cloud cover in regions of strong inversion. You can also bin by low cloud cover. So regions that are dominated by low clouds in the climatology actually end up with fewer low clouds when you warm the warm pool. And if you look at ascent, it's a little bit messier, but which is partially because these regions of these regions of subsidence don't neatly overlap on the low cloud decks, but you don't recover that paradigm of warming in the worm pool leads to more clouds in subsiding regions. You can also look at the top of the atmosphere radiation response. You see something similar. So these regions of strong inversion, you actually get a positive radiative response. Again, the opposite of what would be predicted by QEWTG. You can bin by low cloud cover. You see the same thing. Regions that are dominated by low clouds have a positive response. And similarly, if you bin by vertical velocity, regions of strong subsidence have a positive response. All of these are essentially the opposite of what the QEWTG-based paradigm suggests. One interesting thing you can do is you can weight these responses by the frequency of those bins. So sure, regions of strong inversion have a positive response, but they don't occupy that much space in the tropical Pacific. So red is the probability distribution of the bin of the climatological EIS. So the sum then under each of these curves is the total radiative response, or the average radiative response. So you see a negative response like the Green's function map shows and like we expect, but it's not dominated by the strongly capped boundary layers. It's actually dominated by a broad area around weak or even negative EIS. Same thing, if you look in cloud space, it's actually dominated by regions that are not primarily, that don't have a high climatological low cloud cover. And this negative response that we see in the west to West Pacific warming is dominated by regions of ascent or weak subsidence. So that was a summary, but we can look at the patch responses themselves. And we've already looked at 4 other models, but we can dig in a little bit more in E3SM. So this is the top of the atmosphere response to warming in 3 patches at 100, 140, and 180 degrees east. And what you see if you look in the low cloud decks is that, again, the radiation response is positive. So again, not what you'd expect from the sort of the simple paradigm that the IPCC summarizes. You can look at low cloud cover and see that indeed this radiation response is correlated with low cloud cover. You have decreased low cloud cover in the subtropical decks, more or less, but
Cristi.
on average, when you warm in regions of deep convection. This maps onto EIS, so you get decreases in EIS in these regions. And if you look at Z500, you see that the pattern of EIS matches the pattern of changes in geopotential height. And I haven't plotted T700, but if you look at free tropospheric temperature, it matches the pattern of EIS and Z500 very well. And this is wave activity. So you can do a seasonal average. So this is Z500 in DJF, and you can do a wave flux activity plot based on Plum 1985, and you see strong wave activity, although it's very messy. There's not a simple explanation. JJA, yeah. So my takeaways are that this quasi-convective equilibrium, this convective quasi-equilibrium weak temperature grading paradigm does not explain the response of the subtropical cloud decks to worm pool warming. QEWTG does explain the overall pattern, but it's actually due to the response in the deep tropics, which is where you would expect weak temperature gradient to hold. And you see a broad increase in stability and low clouds in both in both ascent and weak descent region. So I think it's more the balance regime, not the circulation regime, that matters. Are you seeing the weak temperature gradient hold, or are you seeing strong enough gradients to support Rossby waves that dictate which regions have a positive and negative response? So Rossby waves clearly impact the response of the subtropical low cloud decks, but I'm not an expert on Rossby waves. At least to me, there's not a simple explanation for what the wave dynamics is. It's definitely not the great circle stationary Rossby waves from Hoskins and Carroll. So this will probably require wave models on realistic background flows. And this is stuff that was done in 1987, for example. This is Sardeshmukh and Hoskins in 1987, putting an equatorial divergence source and seeing fairly complex wave patterns that do propagate into the low cloud decks. So I don't think we have a simple explanation for these critical regions. That's it.
Great. Thank you, Cristi. Any questions? Please feel free to raise your hand. Unmute yourself. Looks like Maria has a question in the chat if you want to unmute yourself. And if not, I can just read it.
Yeah, I
Hi,
can't see the
Cristi.
chat for some reason.
Okay. Hi, Cristi. We recently quantified spatial controls of local EIS and found the warm pool to matter, but also other regions. Convection also happens elsewhere. See figure 3. She sent a link. Do you have any ideas about how to separate the effect of the weak temperature gradient versus the Rossby waves on local EIS to solve this problem quantitatively?
I don't. My first impulse would be to say we got to run some models. Got to run some wave models on realistic background flows. GFIP is going to be an interesting case study because we have a bunch of models that ran these experiments and we can see how the response differs. But we know that these teleconnection patterns depend a lot on what the background flow is, strength and location of jets and so on. And we know that models have biases in these in their climatology that affects their teleconnection. There's a fairly rich ENSO literature on this, on how these waves propagate and how different model biases might affect the pattern of teleconnections.
Other questions? We have Thurston Moritzen saying he's happy to be wrong, but not really a question.
Thank you.
That was just me wrong, as you said. But yeah, thanks. Thanks for explaining.
Seems like Eric has raised his hand.
Yeah, I just wonder, it seems like the main kind of punchline of a lot of this is the expectation that if the SST gradient, reverses sign in the Pacific, then, there'll be kind of an increase in planetary warming. Is that still something you'd expect given the results that you've presented?
I think so. Assuming that, as Leif showed, the Green's functions are not necessarily stationary, so it's hard to extrapolate in a future warmer world. But the overall pattern still holds that if you have more warming in the warm pool, you have a more negative response. But doesn't seem like that response is really dominated by the low cloud decks. It seems to be dominated by a broad response across the deep tropics. Now, I think where this confusion comes from is because we've also seen this pattern associated with strong changes in low cloud cover in the low cloud decks recently, but that might have actually been the local cooling in the Pacific dominating it rather than the overall gradient. And if you dig to the literature, there's actually two papers. There's a paper by Sarah Kang and a paper by Anna Mackey that have tried to quantify which regions have driven, and I guess Maria's recent paper, that have tried to quantify which regions have driven these low cloud decks, and they find a weak correlation with the warm pool for the recent trend. So the answer to your question is, I would still expect that if the overall gradient changes, you expect a positive feedback in an amplified warming. But I also expect that what's going to be very important is the behavior of the SSTs right under the low cloud decks. And that's this cooling in the Southeast Pacific, which is a very active area of research. I think what's going to happen there is going to be very important. And that might be related to Southern Ocean cooling, and there's a baker's dozens proposed mechanism for what controls that regional cooling pattern.
Great. So we're a couple minutes past the hour. Maria says that that's not true for her analysis and has sent an archive but can't speak up. But if you guys want to hang on to the chat, feel free to. But thanks to our three speakers today, to Ed, Leif, and Cristi. Really appreciate you all coming out this morning, afternoon, whatever time it is where you are. Thanks, and we'll see you in about a month for the 50th.
Thanks, Matt.
Thanks, Matt.